NanoHub U, online instruction.
Hey everyone, welcome to lecture 421. So in the last two lectures, we kind of went over the basics of thermophotovoltaics, and then we actually showed how we can validate a lot of our models that we've built. And now we're going to use the modeling again after the validation to see what are the future directions for this kind of research. And so here's one idea that we've been working on recently called integrated filters. And so the premise here is, in principle, very simple. It's an extension of the 2D tungsten photonic crystals that you saw in the last lecture, but adding an additional filter layer directly on top of this. And so the rationale is as follows, because remember that we had emitter, and then we had filter, and then we had photon recycling back and forth. But what if you combined the emitter and filter into a single object? So here, the advantage is actually then you have pretty much guaranteed view factor of 1. On the other hand, it could adversely affect the thermal emission properties of the tungsten photonic crystal. So it's not necessarily obvious that this would actually help you overall. And the other thing that may be helpful in this case is because you're only emitting the wavelengths that you want, you have much more flexibility in terms of creating a path for the light to travel from the emitter to the receiver, because you never have to worry about sending it back now. Now, of course, there are potentially a few disadvantages to this approach, which would include thermal expansion of the different parts of the system, and then, of course, more complex fabrication. That certainly goes without saying pretty much, but just wanted to mention that we certainly would acknowledge that. And then this basic idea is actually written up in the SPIE Journal of Nanophotonics and was published this year. Just to kind of briefly show what are the advantages. So, of course, you probably remember that last time we had mentioned the world record efficiency for TPV was about 23%. But if you're able to build this sort of structure using realistic materials, which would be tungsten and silicon dioxide and titanium dioxide, so certainly nothing too exotic or super expensive, then you can actually get emissivity for the first type of structure of integrated filters that looks like this. And you can see actually there are actually two curves here. So one is essentially what we calculate out to about 4 or 5 microns. And of course, we had actually calculated out to about 10 microns just to be safe. And you see a big spike in emissivity, which is about 0.8 to 0.9 at the target wavelengths, but the background is very, very low. So you basically have concentrated most of the emission into what we call the green region. And green, of course, is the best region that we want, the highest emissivity. We have some blue at short wavelengths, and then that blue at short wavelengths is actually giving us a little bit of loss because of thermalization. And then at these long wavelengths, these red regions, we of course can't use those photons, so that's complete loss. And so if we actually compare these two structures that we calculated, you can see the first structure, which has an efficiency of 40%, is actually approaching this theoretical limit in these conditions of about 46% for the ideal emitter. And so about 3.8% of the loss is from parasitic emission, which may actually be surprising just looking at this picture, but you actually have a lot of loss from this transition right at this edge here. And then there's a small loss of less than 1% from not having emissivity all the way up to the maximum. And then you have a little bit more loss at short wavelengths, which is coming here at about less than 1%. But then in this second structure here, where you can see we essentially just adjusted the chirping rate, which is basically the rate of change of the periodicity as a function of the depth into the system, then you can see that you reduce the parasitic emission by 1.5%, which is enough to account for the difference between these two parasitic losses and thus the increase in the conversion efficiency. So another future direction besides changing the wavelengths that you're emitting, since we're kind of approaching the limits theoretically, is to change the angle and potentially even the polarization as well. And so if you can change the angle and polarization, then of course what you could do is you could have a very large emitter, which might not even be that hot. But then if you have selectivity over wavelength and direction, then you could actually concentrate the heat onto a small PV cell. And so you don't need to get a big PV cell at this point, but you've concentrated like lots of heat, and then you can efficiently convert that into electricity. It might even give you more efficiency than just the wavelength control alone, and also has the advantage of reducing the fabrication cost potentially as well. And so just to kind of illustrate what is the advantage and where do we really want to even try this, you can see in this graph there are actually 3 different structures or cases that we're looking at. In the first case on the left-hand side, what's happening is we're restricting angles of emission vertically between 2 equally sized emitter and receiver regions. And so what you see actually is probably not surprising, which is just that if the separation D is relatively small compared to the edge length L, then you get pretty much 100% view factor or probability of transmission from emitter to receiver. Now, if you go to the second case, where you have things that are angled towards the end to end, then it's actually not quite as good necessarily for these very small separations, mainly because the geometry is different. The receiver is smaller than the emitter, so it's not a true apples to apples comparison. But you can see, again, that it's actually kind of challenging to get a very high view factor. However, if you direct all of the emission towards the center, no matter where you're starting from, you can see there's a region of high performance for a relatively tight angle control that's less than plus or minus 20 degrees. So that's our best case. And so that's what we would want to focus on if we were designing a system. And so here's like one example of the type of structures that you could use to actually generate this angled emission. And certainly this is work in progress in some sense, although there has been a paper recently submitted on this topic to MRS Advances. What this shows basically is you have sawtooth patterns here and here. And these sawtooth patterns actually create much different field profiles if you have emission in the positive or negative angle direction. And so this is actually also depicted here. And so you can see that for sufficiently small wavelengths where you can actually sense the asymmetry of this periodic system, then you can actually have very high emissivity here and then maybe low emissivity over in the other direction. This is just kind of illustrating this in another way, that you have an asymmetry of about a factor of 3 from this kind of sawtooth structure. So it's a very simple structure and certainly can be fabricated today. And it would give you pretty good control over the angle of emission. And this is just validating some of these results. And so, of course, there are a lot of details that still would need to be worked out for this to be experimentally valuable system, but certainly it's a promising direction to control both wavelength, angle, polarization, and many other factors all simultaneously through advanced photonic crystal design. So in the next and final lecture, I'll kind of wrap up Unit 4 and talk about future directions. Thank you.